So we now continue our study of multivariate calculus by considering limits and continuity of multivariate functions. But first, we need to introduce several concepts. First, we need to extend the concept of an open interval into a region. And we do this by using a delta disk. So if we have a point AB in R2, a delta disk centered at AB is defined to be an open disk of radius delta centered at AB. That is, a delta disk centered at AB is the set of points xy in R2 such that x minus a squared plus y minus b squared is less than delta squared. Right, so if this is our plane region, there's A, there's B, this would be AB right there. So we draw a dashed circle around it of radius delta, and that would be a delta disk. Next, we look at boundary and interior points. So we have a subset of R2, a point P0 is called an interior point of S if there is a delta disk centered around P0 that is contained completely in S. A point P0 is called a boundary point of S if there is a delta disk centered around P0 that contains points both inside and outside of S. This should not be if there is a delta disk. It should be if every delta disk. So if we have, let's say, here's our set. So this is a region within the plane. So let's take blue, right? So consider this point here, right? This would be considered an interior point because I can draw a delta disk that is completely contained within the set. Right, completely contained within the set S. So this is an interior point. Right, so a boundary point is a point in which no matter how you draw the delta disk around it, some is going to be contained within S, and some is going to be contained outside of S. Right, so notice here, no matter how small you draw the delta disk centered around the point, you're always going to have some of it outside and some of it inside. So the difference between open and closed set. So again, we have a subset of R2. That set is called an open set if every point in S is an interior point. It is a closed set if it contains all of its boundary points. So we typically represent open with dashed lines. Right, so this would be an open set, right? Because notice every single point is going to be an interior point. A boundary, or a closed set rather, would contain all of its boundary points. Right now, it is theoretically possible we could have a set that looks like this. Right, this set would be neither open nor closed, right, because it contains some of its boundary points. So it's not only interior points, but it does not include all of the boundary points. Next, the idea of a connected set. So an open set is a connected set if it cannot be represented as the union of two or more disjoint, non-empty, open subsets. And then we say a set S is a region if it is open, connected, and non-empty. So we can draw this, and let's say something like that. So these would be disjoint sets. So connected sets, right? Something like this would be connected, right? Because I cannot represent this as the union of two more disjoint non-empty subsets, right? Because this is contained within the larger circle, right? So if we call this S and this S1, S1 is completely contained within S. So even if I tried to represent this as S unioned S1, S1 and S are not disjoint, which means this would also represent a region. Okay, now we can introduce the calculus of multivariate functions. So if delta is small, then all the points xy in the disk are close to AB. So I'm going to redraw my disk. So here's A, here's B. Right, there's my delta disk around it. So notice that if delta is small enough, right, every single point in here is going to be relatively close to the center AB. So this is analogous to x being close to a in the definition of a limit of a function of one variable. And so we can now define a limit of two variables. Let f be a function of two variables x and y. The limit of f of xy as xy approaches AB is L, which is written this way. Right, so you should notice this is very similar notation. In fact, it's the exact same notation as single variate limits, except now it's an ordered pair approaching an ordered pair and then a multivariate function. If for each epsilon greater than 0, there exists a delta greater than 0, such that the absolute value f of xy minus L is less than epsilon whenever the square root of x minus a squared plus y minus b squared is less than delta. So again, this is a practically identical definition to the single variate limit. So here's the idea graphically. Right here is our point AB, our delta disk around it. This is the image of the disk on the surface, right? So what's basically happening is as this disk gets smaller and smaller, because that's what this condition is saying. I'm sorry. Yeah, that's what this condition is saying. So we can let our delta get smaller and smaller. Then this distance, the distance between f of xy and L, would be less than epsilon. So this distance is shrinking, right? So we have an epsilon neighborhood of L. So we have the two variate limit laws, just like we had the single variate limit laws. So let f of xy and g of xy be defined for all xy not equal to AB in a neighborhood around AB, and assume the neighborhood is contained completely inside the domain of F. assume that L and M are real numbers, such that L is the limit of f and M is the limit of g, and let c be a constant. The constant law says that the limit of c is just c, so this is completely analogous to the single variate constant law. The identity laws. The limit of x is just a, and the limit of y is just b. So what these two laws allow us to do is, if our multivariate function is actually single variate, we can essentially just ignore all of the other variables. So in this case, we can ignore the y component. In this case, we can ignore the x's. So now we have the sum difference law. So the limit of f plus or minus g is just L plus or minus m. So again, completely analogous to the sum difference single variate. The limit of a sum or difference is the sum or difference of the limits. Constant multiple law. The limit of c times f is just c times L. Again, this is completely analogous to single variate. The limit of a constant multiple is the constant multiple of the limit. So the product law. So the product law, the limit of the product of f and g is just L times m. So again, completely analogous. The limit of a product is the product of the limits. The quotient law, the limit of f over g is L over m as long as m is not equal to 0. So the limit of a quotient is the quotient of the limits as long as the denominator is not 0. Then we have the power law. So the limit of the power of a function is the power of the limit. Right? And this is true for any positive integer n. And then finally we have the root law, which states that the limit of the root of a function is just the root of the limit, and that limit must be non-negative if it's an even indexed radical. So just as we did with single variate, we can break multivariate limits into pieces. So let's take the limit of this function. So the first thing we can do is break this up into sums differences. So I'm going to do all of this breaking up into one step. Right, so overall we see it's a sum difference. So we're going to have the limit of simply x squared, right? But that can be used as a power. And now, because it's just of x, this is the limit as x approaches 2. Then we're going to have limit of product, so it'll be minus 2 times the limit x approaches 2 of x, then times the limit as y approaches minus 1 of y. Then we have plus 3 times the limit as y approaches negative 1 of y, and that whole thing will be squared, minus 4 times the limit as x approaches 2 of x, plus 3 times the limit as y approaches negative 2 of y, and then minus the limit of 6. And now this is simple calc 1. Right, we get 2 squared minus 2 times 2 times minus 1 plus 3 times minus 1 squared minus 4 times 2 plus 3 times, I'm sorry, this here should have been a minus 1, minus 6. So we get 4 plus 4 plus 3 minus 8 minus 3 minus 6, and that is just simply negative 6. So now for this function, I'm not going to go through all those steps again. Basically, we can just plug in x equals 2 and y equals minus 1 into the function. So this limit becomes 2 times 2 plus 3 times minus 1 all over 4 times 2 minus 3 times minus 1. 4 minus 3 is 1. 8 plus 3 is 11. So this limit is 1 over 11. Now we wish to show that this limit does not exist. All right, so the basic idea behind this is if we look at single variate, right, we were on a number line. Let's say this is our limit, or our what x is approaching, right? Well, there's only two ways that we could approach a. We could either come in from the right-hand side, right, or we could come in from the left-hand side. The same is not true when dealing with multivariate, because now we have a region. So let's say this is our point AB that we're trying to approach. Well, how can we approach it? We can come in from above, we can come in from below, we can come in from the left, we can come in from the right, we can come in all these diagonals, right? We can come in this way, we can come in that way, right? In theory, there's an infinite number of ways that we can approach now this AB. Well, that's a problem. But here's the beautiful thing. No matter how you approach AB, the value has to be the same, right? F has to approach the exact same value. So to show that this limit does not exist, we just need to show that there are two different directions. There are two different ways to approach 0, 0, such that these are not the same value. Well, let's first consider approaching the origin along the line y equals 0. So then the limit of 2xy over 3x squared plus y squared would become the limit of 0 over 3x squared. Well, that limit is just 0. Okay, well now, what happens approaching along the line y equals x? Well, now our limit would be the limit of 2x times x over 3x squared plus x squared. So this becomes the limit of a half, which is 1/2. Now notice, these two values are not the same. So since we don't approach the same value, since we are approaching different values, the limit does not exist. Right, so now let's discuss continuity. Well, we're going to see that the definition for continuity is analogous. So a function f of xy is continuous at a point AB in its domain if the following three conditions are satisfied. And you should compare these three conditions to the three conditions of single variate. So the first condition is f of AB must exist. The second condition is the limit as xy approaches AB of f of xy must exist. And the third condition is the limit of x as xy approaches AB of f of xy must equal fab. So let's show that this function is continuous at the point 5, negative 3. So the first thing we have to do is show that f of 5, negative 3 is actually defined. It exists. Right? Well, this will be 3 times 5 plus 2 times negative 3 all over 5 plus 3 plus 1. Right? Evaluating a multivariate function is the same way as we evaluate single variate. Right? So this order tells us the order in which this will appear. So wherever you see an x, you're going to put in a 5. Wherever you see a y, you're going to put in a minus 3. So this will give us 15 minus 6, which is 9, over, sorry, this should have been a minus 3, over 3. So the value is 3. That definitely exists. So the first condition has been satisfied. So we can check the second and third condition simultaneously. Now we just take the limit as xy approaches 5, negative 3 of 3x plus 2y over x plus y plus 1. Right, well, according to the limit laws, we're going to get 3 times the limit of x plus 2 times the limit of y all over the limit of x plus the limit of y plus 1. Now remember, x is approaching 5, so we'll get 3 times 5 plus 2 times y is approaching negative 1 all over 5. I'm sorry, y is not approaching negative 1. It's approaching negative 3. 5 plus negative 3 plus 1. And you'll see that this is 9 over 3, which is 3. Since these two values are the same, not only does the limit exist, but it equals f of 5, negative 3. Therefore, our function f of xy is continuous at the point 5, negative 3. All right, so a theorem, there's actually 3 parts to this theorem. First, if f and g are continuous at x naught, y naught, then so is their sum. If g of x is continuous at x naught and h of y is continuous at y naught, then the function defined as g of x times h of y is continuous at x naught, y naught. And finally, let g be a function of 2 variables from a domain D to a range R. Suppose g is continuous at x naught, y naught, and define z naught to be g of x naught, y naught. Now let f be a function that maps the real numbers to the real numbers, such that z naught is in the domain of f. Lastly, assume that f is continuous at z naught. Then f, remember this is composition, g is continuous at x naught, y naught. So this is a composition. Now this has to work a little bit differently. Right, so in this case, f of g makes sense, right, because g of x, y is going to give you a single value. And since f is a single variate function, f of z makes sense. Notice, however, that g of f would not make sense, right? This is not defined because f is a single variate function. This is going to give you a single value, call it y. Well, g is double variate, right? So you can't have g of a single value. You need two values. So unlike in single variate, remember in single variate, the composition existed no matter how you did it. It's just the order mattered, right? You wouldn't necessarily get the same value. In multivariate, not only may you not get the same value, but it may not even be defined if you switch the order. And of course, all of these discussions, so the discussion that we just had, naturally extends into functions of more than two variables. So you can naturally define a three-variate limit, except now we're considering what's known as a delta ball. And then the definition would be defined identically for limit. All right, so that concludes our look at multivariate limits.